In this video, we are going to discuss the graph coloring problem using backtracking method. Here we have a given graph G with nodes A, B, C, D or vertices A, B, C, D, and different edges are A, B, A, C, B, C, B, D and C, D. These are the various edges of the graph. Now also we have given a set of colors. Let's say set of colors S is equals to red, green and blue. These are the three colors. Now we have to color the vertices using these three colors in such a way that no two adjacent nodes have the same color. So that is the problem. Now we will solve this problem using backtracking, and for that, first of all, we will create the state space tree for given graph. To create the state space tree, we will take first one arbitrary node. This is known as the root of the tree, root of the tree. Then we will randomly pick up any one of the nodes from the graph. Let's say we take node A and we will color this node A. We can color this A with the color R or red, or we can color the node A with color green, and we can also color that node using blue. That is, A has three options to color, either red, green or blue. Now once we explore A, then we will explore the adjacent node or rest of the nodes in the graph. Let's say this time we consider node B. We will go exploring A, and from A we will color B with color red. B can be colored using green and B can be colored using blue. But however, we can see that A and B are adjacent nodes. That is why they both cannot have the same color. So we will not consider this one as a valid branch of the tree and we will remove it. Then accordingly, we will go to the next node. Let's say C is the next node, and C can be explored either from this node or from this node. We will first consider the green node to explore. So if I take C, either I can color C with red color, C with green color, and C can be colored using blue color. Now there is a link here. So now if I see A and B are adjacent nodes. A and B are adjacent nodes. A and B cannot have the same color that we have considered here in the earlier case. But again, B and C are same adjacent nodes. B and C cannot have the same color. That is why this color green for B is not possible. Similarly, C is also adjacent to A. So A and C cannot have the same color. Here A has the red color, and this node is also not a valid node because it cannot have the red color. So D can be colored as red, D can be colored as green, and D can be colored as blue. Again, C and D are adjacent. C and D cannot have the same color, so this is not a valid branch to explore. And similarly, D is also attached to B. B and D cannot have the same color. So in this branch, B has the color green. So D cannot have the green color. So this is also not a valid branch. After D, we do not have any node to explore. So if we consider this branch, then what we will have? We will have a solution. A will go to B, then from B we'll go to C, and from C we'll go to D. Now the various colors are, if we consider this is one solution, one valid solution, then the colors will be solution 1 is equals to A is colored as red, then B is colored as green, C is colored as blue, and D is colored as red. Okay, RGBR is one valid solution. Similarly, we can now explore this node because there is a node available here which is not yet been explored. So in this branch, we will let me draw this side. So B, after B, we'll explore C. C can be colored as red, C can be colored as green, and C can be colored as blue. But however, what we can do, B and C are adjacent nodes. That is why we cannot have the same color. So this blue color is not possible for this node. So we can similarly, C is also adjacent to A having color red, and this C red is also not possible. So we have only one solutions or one path left out. Now we'll explore this node C with green color. This is the only possibility of coloring C in this case. We'll consider node D. D can be colored as red, D can be colored as green, and D can be colored as blue. But however, C and D are adjacent nodes. This coloring D with green is not possible. Similarly, E is also attached to B. B is blue. That's why this color D, node D cannot be colored as blue. So that is why we have one solution here with color D colored as red. This is the possible solution. So according to this solution, we have a solution here from A to B, B to C, and C to D. So the solution is, solution number 2 is equals to red, then blue, then green, and then R. So this is another solution. Similarly, if we explore the other nodes means now this node with node A with color green now can be explored. Similarly, node A with color blue can be explored. If we explore these two branches, then we will get two solutions here and two solutions here. So this is the complete state space tree for the problem, and we have expanded all the nodes which are possible to expand, and finally we found out these solutions. This is the first solution, second solution, third, fourth, fifth, and sixth solution. According to the first one, A is colored using red, B is colored using green, C is colored using blue, and again D is colored using red. Similarly, in this solution, A is colored using red, B is blue, C is green, and D is again red. So this is another solution, and these are all possible solutions for the graph coloring problem using backtracking. Here, when we follow the path of this tree, then what we do when we go here, say we are in node C, and see there is no possible path for the solution. That's why we will come back to the previous node, its parent B, its parent B. Then from B we'll try to explain. Again, when we come back, when there is no path from the C, then we come back to B. That is called actually the backtracking. So uh, whenever there is no solution found, then we will backtrack to the previous point, that is the parent, and then again we'll start exploration. So this is the way how we solve the graph coloring problem using backtracking.